Alright, let's talk about some more isomorphism theorems. Actually, I think we just have one more. Yeah, and then we're going to talk about other stuff. So, anyways, before we get to the second isomorphism theorem, we have to establish some background knowledge. So, if H is a subgroup of G and N is a normal subgroup of G, then H intersect N is a normal subgroup of N. And let's see here, how do we prove this? So let's suppose we take some element X in H intersect N and H in H. So what we want to do is we want to check the normality thing. We want to make sure that if we conjugate... Wait. No, this isn't right. Statement's wrong. I must have written it down wrong or something. But yeah, this is going to be normal in H. I mean, it's probably also normal in N. Well, okay. Certainly, if we prove this for the case of H intersect is normal in H, then in particular, if we let H equal N here, then we'll have N intersect N is normal in... Oh, but I see. Okay, so maybe if we have just another subgroup H. Anyways, this is what we're trying... Yeah, okay, yeah. There's something else later on that we're going to get to that will show this. And so this is what we're trying to prove. So if we have X in... Oh, by the way, I have the light over here now. I'm still experimenting with the different lighting setups to see what works and what doesn't work well. So, anyways, bear with me while I figure that all out. But for now, we're going to just prove some stuff and do some math. And so, let's see here. Hx, H inverse. Let's see here. It's going to be in... So what we want is we want Hx, H inverse to be... For this to be normal in H, we need Hx, H inverse to be in this intersection. So it's enough to show that it's in H and that it's in N. Well, certainly it's in H. And that's just because X, H, and H inverse are all elements of H, and H is a subgroup. And, well, if we do Hx, H inverse, Hx, H inverse, now if we use the normality of N and G, then what we're doing is we're taking an element, X is in N, so we're taking an element of N and conjugating it by an element of G. And so this is going to be an element of N. Because, yeah, that's what normality means. And so, yeah, now that Hx, H inverse is in H, and it's in N, then it's in the intersection, and that means that H intersect N is normal in H. And I'm not going to write the rest of that stuff because I'll take another line, and I don't feel like using another line for that. Proposition, other one, Hn, as above. This is going to be the collection of all products of the form H and H and N and N. This is in G, and turns out Hn is equal to Nh. Oh, by the way, here, typically with set notation, it's like you have like what the things in the what the elements in the set look like, and these other conditions here. Interesting thing I've noticed here there seems to be a divide where if you're if you study algebra, you tend to write this line here to mean this is a collection of all elements that look like this. These are what the elements look like, and these are what the elements satisfy. And so they use the line to divide that. But then if you're an analyst, it seems like people tend to use the colon. So it's just a small notational thing. Hopefully didn't cause any confusion, but I tend to use that because I tend to like analysis. So this is our proposition. And we're not done with this proposition. Also, H and N are both subgroups of Hn. And if N is normal in G, then N is normal in Hn. I'm trying to think, are we assuming throughout this problem that we have normality? I guess not. So anyways, let's prove this. So proof. So let's start with this, Hn equals Nh. Hn equals Nh because if we take an element Hx, where H is in H and X is in N, then we can write this as Hx H inverse H. Yeah, so in this case we are actually, it looks like we are taking N to be a normal subgroup throughout, and so this extra statement here is redundant. So anyways, because what we do here is we have Hx H inverse. This is an element of N, and H is obviously an element of H. This is in NH. So remember, this is any element of Hn, and so Hn is contained in NH. Then likewise, you do the same argument but backwards. Then NH, or with you flip it, and you get NH is contained in Hn. So equality holds. Okay, so that's that part of the proof. How about for subgroupness? So to prove that Hn is a subgroup of G, let's see here. If we take H1x1 and we multiply H2x2, where of course H1 and H2 are elements of H and x1 and x2 are elements of N, then we write this out as H1, and then we write H2 H2 inverse, and then x1 H2 x2. And so H1 H2, well, obviously this is going to be an H. And now here we have H2 inverse x1 H2. And so we're conjugating x1 by H2 inverse. And so this is in H. And so this is something in H times something in H times something in N. And so this is in Hn. I'm going to erase this to give myself more room, but that's the point. The point is that when you break this up like this, you'll get this times this, which is something in H, and then this, which is something in N. Okay, so that proves closure under multiplication, and for closure under inverses, if you have hx, and we look at its inverse, then hx inverse equals x inverse h inverse, but this is in nh, which we just proved is equal to hn. So that's why we proved this one first, because we actually used it to make our lives easier here. Okay, so now hn is closed under inverses and it's closed under products. And I've been kind of skipping over this a lot, but you can actually just, you don't even have to prove that it contains the identity element, because now we automatically have it. Because, well, I mean, so long as a set isn't empty. So I guess, yeah, maybe sometimes you need to prove existence of like some element in there in order to do that. But we know that Hn is not empty because H and N both contain elements, say the identity. But anyways, what happens is you take any element of Hn, and by closure under inverses, that element's inverse is in Hn. And then by closure under multiplication, if you multiply those together, then that will give you something in Hn. But if you multiply something with its inverse, you'll get the identity. And so that means that the identity is in Hn. And so typically you can get around proving that the identity element is in a group, but it's also typically easy enough that, like, why not just spend the extra time to write it down? Okay, so let's see here. I'm going to draw a picture now. And so here's what we have. We have a group G, and then we have Hn, which is NH. Then we have H. This is N. This is H intersect N. So anytime I have a line here, that means subgroup. So I'll actually just write that. So we have Hn and NH. These are subgroups of G. H is a subgroup of Hn. Do we prove that? Oh, here, first of all, yeah, did we prove this? Oh, I don't think we finished this proof. Anyways, let me continue what I was doing here. And so H is obviously a subgroup of Hn because it's a subgroup of G, and it's contained in Hn because E is contained in N. So this is just anything that's in H is in Hn, because you take that element and you multiply it by the identity. Okay, so that's a subgroup. Then H intersect N, the intersection of any two subgroups we know is a subgroup, and it's going to be contained in N, and so it's a subgroup of N. And then we proved up here that we have normality here. And then we also need to prove that N is normal in NH. Okay, I don't have a script to go off of for this part, so let me here. Give me a second. Let's just try the. So first of all, let's write clearly H and N are subgroups of Hn. Lastly, so this is going to be boxed off by itself. And lastly, What are we doing? We want to prove that n is normal in Hn. So let's take, so let Hn be in Hn. No. So we want for all n in n, for all hx in Hn, what happens when we conjugate? Hx times n times hx inverse. This is going to be hx n h inverse x inverse. So what do we want? Nope. Don't look at that. That's wrong. Don't do that. It's x inverse h inverse. And so we want this whole thing to be an n. No, we want this to be an Hn. So we want this to be something in h times something in n. So let's see here. On the inside here, this is x and x inverse. So what we're doing is we're conjugating n by an element. Oh, wait, no. This is obvious. This is obvious because right. Because n is a normal subgroup of G. And so n is going to be so here, let me write out why this is obvious. For all n and n, for all G and G, we know that G and G inverse is in n. And in particular, that thing we know because of normality of n. And so in particular, if instead of for all G and G, for all, we'll say G in Hn, we have G and G inverse is in n. And so n is normal in Hn. So really what happens is if you've got a subgroup, if you have a normal subgroup of a group and you restrict this subgroup to you restrict this group to some other subgroup which contains the normal subgroup, then that normal subgroup is normal in this group, just because you're considering this, it's a weaker condition. Okay, so here it looks like I do not have time to actually prove the second isomorphism theorem, so I will leave that for next video.